Okay, so when you hear the term finite state machine, or in short FSM, there are three things that, like, there are three words, right? Finite, state, and machine. So let us take a look at what each of these words signifies in our overall FSM design process. So I'm going to highlight them individually so that we can take a look at what each of these actually mean. So finite, the word finite essentially is being used, is being used to indicate that there are going to be finite number of states. Just as we had finite number of states in our counter design problem, you remember in our 3-bit counter design that we just did, we had very finite number of states in our counting pattern. We had we didn't have all 8, but we had 7 states, each state representing the output of the counter. Just the same way, a finite state machine has finite number of states. That's why we have finite. Then state, what does state mean? Just as we did for the counter, the state of the counter. What is the state of the counter? Well, whatever it's counting right now, right? So if it is at 5, the state of the counter is in 5. That could mean some state 2, but that is one state. So the current outputs of all flip-flops in the FSM dictate what the state of the finite state machine is. So that's the state. How about machine? Well, a machine is being used here to indicate that our FSM will go from one state to the other state, and this could depend on some inputs, or it could also depend on the sequence of past inputs. So the machine is used to indicate that we are go from one state to the other depending on inputs or sequence of past inputs. And there are two types of finite state machines. In one, we don't use the inputs, we just use the sequence of past inputs. And the other, we include both inputs and sequence of past inputs. So there's a differentiation there. So that's why machine. Now a little bit of recap in terms of our generalized block diagram for sequential circuits, aka state machines, because all they're doing is they are going from current state to the next state. That's all they're doing, one state to the other, and that could depend on, like I said, it could depend on inputs, or it could depend on the sequence of past inputs, which is already in the next state, right? So it's already in the current state, which is being fed back. So if you look at this particular diagram here, they are outputs, right? If I asked you guys, what do these outputs depend on, what would you say? So let's ask that question. What do these outputs depend? What do the outputs depend on? Or when do the outputs change? Now for answering this, I would need to track back from these outputs to the input side. So if I track back, I see that this could be due to the current state changing, or this could be due to the inputs changing. Remember, this block is a combinational network, right? So as soon as this changes, that changes. As soon as this changes, this changes. That's a combinational network. You are right. Yes. So when the combinational network changes, right? So one possibility is because of the current state, right? So let me write that over here. Outputs could change when Q changes. So that's current state. You guys see that? So let me color code this now. This is essentially saying this changes, current state changes. Because current state changed, that changed. That's one possibility, right? So we are essentially using that arrow there. The other possibility is right here. Outputs could change when inputs change or Q changes. So both this as well as that, both of them could contribute to that. Let me highlight this in green, for example. So those are the two possibilities here, right? Outputs over here, outputs of your finite state machine could change when the current state changes. And Preston, you're absolutely right. The current state changes with respect to the clock. Absolutely right. Because all these guys, let me also draw that. All these are, come on. These guys are flip-flops. And this is a combinational network which has no memory. So the flip-flops are triggered by a clock. So the current state changes to the next state soon after the active edge of the clock. And that could later change the outputs, right? So that is, outputs could change when the current state changes. The other possibility is the outputs depending on both these things, the current state as well as the inputs. So outputs changing when the inputs change or the current state changes. So this classification here essentially is the classification for the two popular finite state machines that we have. One is the Moore finite state machine. And the other is the Mealy finite state machine. Now let's talk about their synchronous nature, right? So I'm next talking about their synchronous nature. What does that mean? That means I'm talking about the changes in the output, whether they are synced with the clock or they are not necessarily synced with the clock. So what do you guys think for the Moore finite state machine? Are the outputs in sync with the clock? For the Moore finite state machine, right? The Moore finite state machine says outputs can change only when Q changes. When can Q change? Q changes, the current state changes only when there is an active edge on the clock, right? So for a Moore finite state machine, the outputs can change only with respect to the clock, which means this is going to be a synchronous finite state machine. Now let's talk about Mealy. In the Mealy finite state machine, is it synchronous or it does not qualify as synchronous, which means it is asynchronous. Now look at this. The outputs for a Mealy, it's not, right? Because it breaks in one case. Outputs could change when input changes. You guys see that? When input changes, who controls when the input changes? Well, the user controls when the input changes. Which means the Mealy finite state machine is not necessarily synchronous because it depends on the inputs directly. So this actually is an asynchronous finite state machine. Now you could argue that what if inputs are not playing a role? Well, if inputs are not playing a role, then Mealy finite state machine and Moore finite state machine are essentially the same thing, and we classify that as synchronous. So the only differentiation over here between the finite state machines is the fact that one depends on inputs and the other depends on only the current state, right? So Mealy depends on inputs as well as the sequence of past inputs. Moore only depends on sequence of past inputs or the current state. All right, questions here. So it's very important to distinguish between these two finite state machines, and more importantly, the reason what differentiates them, right? That dependence of inputs on two things: inputs and sequence of past inputs. All right, we will see more examples about this. So you guys will, see this play out, this dependence play out many times. Let me move forward here. Now, in our counter design, when were we going from one state to the other? When were we going from one state to the other? Question mark. When the clock changes from 0 to 1. Absolutely, right. So, well, instead of, I'm not going to limit that from 0 to 1. So when the answer is based on clock, right? So that was based on clock. Now, what if I say, let us design things that go from one state to the other, not based on a clock, but based on something real. For example, coins, pushing of buttons in an elevator, sensors in an elevator, keyboard input to a computer, memory in a computer. So you guys see that change from one state to the other in a counter was happening automatically because we said, okay, let's make this transition from one state to the other based on a clock. But I could also switch this into a more interesting user application in which I go from one state to the other when something real happens. For example, when somebody inserts a coin into a vending machine, the vending machine goes from one state to the other, having no money to having some amount of money, right? So that's kind of where we are going with this, right? So that state transitions now are being controlled by something real, something that user is controlling. Earlier, we had only the clock, right? That was our triggering or state transition dependence, the clock, the active edge of the clock, essentially. But now, for our finite state machines, we could have examples such as a vending machine, an elevator, or a computer, which is essentially the biggest finite state machine we can think of. Now, for a vending machine, What are some inputs and outputs? Well, the inputs could be coins and user pressing some buttons. The output could be the vending machine actually giving the user some food, and then if there is some change to return, it also gives back some coins. In the elevator, the input could be coming in from the buttons or sensors in the elevator. The outputs could be lights and motors activating the up and down movement of the elevator. For a computer, the inputs could be coming from the keyboard, network, memory, or a hard disk. The outputs could be your monitor display, again on a network because it can operate as input and output both. And what is the controller there? Like, what is making sure that all these inputs and outputs are behaving as the user desires? It is the microcontroller, right? Which is essentially invisible to the user because they only see the inputs and outputs. They don't see what is going on in the background, which is what is making everything go from one state to the other. So we will see that computer is actually our biggest finite state machine, which is, invisible to the user. So what is that? The control unit, right? The control unit of a computer is the biggest finite state machine. Let's take a look at an example. This is your first finite state machine problem. Let's take a look at this. In this, we are trying to design a machine that is an odd parity checker. Odd parity checker. You guys remember what odd parity means? Number of ones. If they are odd, that is indicative of odd parity. So what we want our finite state machine to do is to assert the output. In other words, make the output 1 whenever the input bit stream has odd number of ones. So imagine a bit stream coming in, and if that bit stream, this is kind of important, you guys. So let me take up an arbitrary bit stream here. I will say my input is here and my output is here, right? I want my output to be a 1 when there are odd number of ones in the input. So let me just arbitrarily put up an input sequence, right? So this is a 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, right? So I've just put up like an arbitrary input bit stream, right? And let me see. This is happening at T0. This is getting into the machine at T1. This is in at T2 and so on, right? So we are essentially increasing time as we go through here. The output is what? Make output equal to 1 when only when there are odd number of ones. Sorry, there was. Did I miss something here? Now let's see. Now let's see what happens when the machine sees the 0. What should be the output when it sees 0? Soon after it sees 0, the output is going to be 0. Perfect. How about when it sees 1? 1. You got it. Guys got it. Why? Because the number of ones it has seen so far is 1, which is an odd number. So the output goes to 1 here. All right. Next one. What should the output become? 0 is perfect because now we have even number of ones. So it's no longer an odd parity. It has become even parity. So it goes to 0. And similarly, what happens here? Still 0. What happens here? Goes to 1. What happens here? Goes to 0. What happens here? Still 0. What happens here? Goes to 1. What happens here? Goes to 0. No, sorry. It's still 1 here. Here it goes to 0. You guys agree with this? How many inputs do I have? How many bit input do I have? And how many? Oh well, 9 because I have taken 9 examples. But is it a 1-bit input or a multiple bit input? 1 bit at a time, right? So my input is essentially 1 bit input. Right, 1 at a time. So it's just 1 wire, but the value on that wire is essentially changing with respect to time, right? So it's a bit stream. It's 1 bit getting streamed. How about the output? Is it output is 1 bit? Can I say that? The output is also 1 bit, right? Yes, absolutely right. Sometimes it shows me a 0, sometimes it shows me a 1. So if it's showing me a 0, that means that I have even parity so far on the bit stream coming in. If it shows me a 1, that is odd parity check. So what I have here is a finite state machine in which this is my input stream, input coming in as a 1-bit input streaming in, and I have my output here, and in the middle I have this odd parity checker that I need to design. I have not yet designed it, right? I have not yet designed it yet so far, but at least I know the objective. I know the objective of how should the output change based on the input coming in. All right, questions about this, like the description of the problem? Oh, yeah, absolutely. We are going back. We are absolutely going back. All right. So I'm going to assume that you guys were clear on that. Now let us talk about the state diagram. Whenever we are designing a finite state machine, the first step that we do is to draw the state diagram, just as we did for our counter design. And our state diagram has circles and arrows or arcs. Our circles indicate the states. And there are only 2 states that I'm interested in this particular example. The state in which my output is 0. In other words, the input is having even parity, right? That's right here. Even parity, output is 0. And the other state that is possible is my output has odd parity. It has checked odd parity. The state is odd parity and the output is 1. Now notice how we are writing the output. The output is right now dependent on the state we are in. Output right now is dependent on the state we are in. So 2 states, even state, out, and odd state. To kick things off, you use a reset button. So reset is sort of like initialization of your state diagram. Where do you start at the beginning? So there is a reset that comes into the even state, right? So at the beginning, you're assuming that you start off as even parity. And when you come to the state, there are 2 possibilities on your input. The input is 1 bit, right? So if you are in even state and you get an input of 0, you stay in that state. This is called a self loop. You are in the even state and you get a 0 on the input, you stay in the even state. If you get a 1, suppose you are in the even state and you get a 1, you go to the odd state. So you see, where are we writing the input? We are writing the inputs here. Right? So the inputs are causing the machine to go from one state to the other. Where are we writing the outputs? Let me highlight your outputs here in, say, blue. Output, output. You guys see that? And this is our state. I can also call this present state. PS, present state. So if currently, if you are in the even state, you could get a 0 or you could get a 1. If you are in the odd state, you could get a 0, self loop, or you could get a 1. You go back to the even state. If you are in the even state, your output is 0. And if you are in the odd state, your output is a 1. Questions about how we drew the state diagram? Two circles for the two states. Two arrows coming out of each state, depending on whether you get a 0 or a 1. We are writing inputs on the arrows, the transitions, and we are writing output of the machine inside the state. So output depends on the state. Hold on. Output depends on a state, right? Output is written in the state. Output depends on the state. Can you guys tell me what machine is this? Moore, absolutely right. You got it. So this is a Moore machine. In a Moore machine, you will find the outputs inside the state. For a Mealy machine, you will find the outputs on the arc because it depends on both the inputs and the state. Later, more about that later. All right, let's talk about this symbolic state transition table next. So in the state symbolic transition table, we use symbols. What are the symbols? Even is a symbol. Odd is a symbol. Even, odd, all of these are symbols, right? So there are 4 possibilities representing the transitions in the state diagram. The first possibility is your present state could be even and your input could be a 0. Your present state is even, your input is a 1. Your present state is odd, your input is a 0. And your present state is odd and your input is a 1. Now, if you are even right now and you get a 0, you stay at the even state, right? So if you are here and you get a 0, you stay there. If you are even and you get a 1, you go to the odd state. If you are here and you get a 1, you go to the odd state. And Similarly, you can fill out the other two cases as well. I'm sure you guys can do that pretty easily, right? So present state, input, next state, output. Now, just to make things a little bit simpler for me, I will name them a little something. So I'll say PS for present state. So let's see. And I will call my input W. I will call my next state NS, and I'll call my output Z, right? This is just for the sake of me not having to write really long words, right? Present state, W, next state, output. What is the output dependent on, right? The output, you see the 0 here and the 1 here, is dependent on the present state. It is not dependent on the next state, right? I'm not writing 1 because it is going to go to 1. I'm writing a 0 here because it is 0 right now, right? So the outputs are dependent on the present state. You see this? 0, 0, 1, 1 because it is even, even, odd, odd. You guys see that? All right, questions about the state symbolic state transition table. Your present states could be even or odd. Your input could be a 0 or a 1. Your next state is even or odd depending on your input as well as on your present state. And your output depends on the present state only. Questions here? All right, let's zoom out here. And now let's talk about how do you go from a symbolic state transition table to encoded state transition table. Now, this is essentially the user coming in and saying, I don't understand even odd, I understand zeros and ones. Because my flip-flops don't take the input of even, they can take an input of 0. So essentially, we are going to go from a symbolic state transition table to encoded state transition table, which involves encoding the states into zeros and ones. So we could say even is encoded as a 0 and odd is encoded as a 1. Doesn't have to be. You can switch that around. But if I do this, even is 0, odd is 1, then my even, even, odd, odd goes to 0, 0, 1, 1. My even, odd, odd, even goes to 0, 1, 1, 0. Everything else is the same, right? So the state symbolic transition table is a representation of the state diagram. And from the symbolic state transition table, we go to the encoded state transition table by taking in the states and encoding them as zeros and ones in bits, in the form of bits. You see this, different encodings will have different costs. In other words, it is user dependent, right? So I could have picked the opposite encoding as well. Questions about the encoded state transition table. Now let us do an exercise here. What I'll do is I will say this is, say, PS, and this is W, this is NS, and this is Z. Can you guys tell me an expression for Z in terms of the inputs here? An expression for Z and the expression for next state. A logic expression. Z equals PS and next state equals present state exclusive or W. That is absolutely right. So Z equals present state, because if you notice, this exactly matches that. That is correct. Next. For next state, we are looking at this column and how does it depend on these two. If we see, this is essentially 0, 0, 0, 1, 1, 0, 1, 1, and the output is 0, 1, 1, 0. Same, different, different, same, right? So that's a exclusive OR operation. So you guys are absolutely right. Next state equals present state exclusive OR W. So I've got the two expressions here that I would need to build this state machine. And I'm using the D flip-flop to do this. I'm using D flip-flop to do it. For most of the finite state machines, the use of D flip-flop is the easiest just because of its very simple characteristic equation. What is the characteristic equation for a D flip-flop? Q plus equals D. In words, it means whatever you want your next state to be, just provide it as the input, D, right? So you see what I did here? I said D equals present state exclusive OR W. What did I have on the previous slide? I had next state equals present state exclusive OR W. That's the expression that you guys helped me write in on the previous slide. You see how I transitioned this to this. I could only do this because of the characteristic equation of the D flip-flop, which is next state equals D, right? Right here. So it's very simple to do this, if you have a D flip-flop. So what are we saying? Next state is D, present state is present state, right? So next state is this, present state is present state, and the W is the input. And the other expression that you guys helped me write was output Z equals present state. That's right here. We are essentially going to represent this using a diagram. You see this? This is your exclusive OR gate. Your input is right here, W. Your expression at this point is going to be what? W exclusive OR present state. This is your positive edge triggered D flip-flop with active low reset. The active low reset is essentially being used to kick things off. And what is the output? Output equals present state. So that's right there. So the output of the D flip-flop here is both the present state as well as the output Z or Q, whatever you guys want to use. So how are we, what is this, right? Your input bit stream is coming on this wire. It goes through the exclusive OR gate into the D flip-flop, and the output is over here, right? Now let us suppose we start things off as reset, right? When you make this reset active, this guy goes to a 0, right? The output goes to a 0, and you have a 0 over here, and that is going to get compared with the new input coming in, right? And at the active edge of the clock, the positive edge of the clock, this output keeps changing depending on the odd parity check discussion that we had earlier. Now, if you were to design this using a T flip-flop, you could have done that as well. The only thing that works here is, the only thing that you need to take care of this over here is, the D flip-flop, when you implement a D using a T, you get an exclusive OR because of that flip-flop conversion that we looked at earlier. So you could essentially convert this D flip-flop into a T flip-flop and get it to work exactly the same way. You still have a positive edge triggered odd parity checker. Input coming on here and output coming on here. Actually, you know what? Let me show you guys how to do that in a slightly different manner. What I'll do is I will add a page here before, and I will say present state W, next state output Z, right? Now I will also add one more column here for T, right? We had 0, 0, 0, 1, 1, 0, 1, 1, and we said the next state should be even, odd, odd, even, right? So if we were to design this using a T flip-flop, this is my Q, right? This is my Q plus. How do I go from Q to Q plus using a T, right? So what should I write here? Here, what should I write over there? Am I toggling or am I not toggling? 0, 1, 0, 1. Don't toggle. That's absolutely right, because 0 is going to 0. No toggling. Yes toggling. No toggling. Yes toggling. Right? Now, if you see this, what does this match? This matches this. Right? So you could say T equals W. That's exactly what we did here. So in case you are wondering if this is correct or not, we just looked at the fact that it is, right? So you could implement your finite state machines using any flip-flop you want. D happens to be the most straightforward just because of a simplistic characteristic equation. But you don't have to do it using D all the time. All right, let's take a look at the timing behavior for input with respect to the clock for the output. What matters over here is what is the value at the input at the positive edge of the clock, right? This is quite important for you guys to understand here. That because our flip-flops are positive edge triggered, right? So if you look at this, the input, so the output starts off at a 0 because we reset it, right? We reset it here. The input is a 1 to begin with. So the flip-flop is going to monitor the input at the positive edge of the clock. And if it is a 1 there, your output is now going to be a 1 because that is odd parity. And then again, it is going to look at it over here. 0 when the positive edge happens. So no change in parity, still a 1. 0 when the positive edge happens, no change in parity, still a 1. A new one has come in at the positive edge, which makes it even parity, so the output goes to 0, and so on with time. Now, one thing that I want you guys to notice here is this. What if our input went from 0, 1 here to a 0 and a 1 and a 0 and a 1 and a 0 and a 1 and a 0 there? What would happen then? Would the output change at all? No. So I'm saying that, let's see. I'm saying that over here, it is a 1, and over here it is still a 0, just as it was earlier. However, in between the positive edges, suppose the input went haywire, 1 0 1 0 1 0, right? Would the output change? You got it. Yes, it would not change at all, right? Because it is clock dependent. It only looks at the input when the positive edge of the clock happens. You guys see that? So this finite state machine is going to do our odd parity check exercise, but it is going to be monitoring the input bit stream coming in only at the positive edge of the clock. You guys see that? All right. Now let's talk about something else. This input, right? So suppose I attach this input to a switch and I'm asking somebody to physically push the switch up and down. And this is connected to a crystal oscillator, high-speed crystal oscillator, say 100 megahertz or even 100 kilohertz. This is a human. Would I need to worry about this problem? Would I need to worry about the problem that I'm only monitoring the input at the positive edge of the clock? I don't need to worry about it. Why? Why do I not need to worry about it? You got it. The clock is too fast, right? So this is the thing that I'm trying to convey here, that the clock is very fast compared to the human inputs that we see, right? So even though this problem exists, we don't worry about it because the clock is much faster than the inputs, right? So humans are slow. All right. So all of this is kind of captured over here. You know, you guys, isn't quartz. So when I talk about clock, I'm talking about, something that is changing at a 100 kilohertz or 50 kilohertz or 100 megahertz, right? Much, much faster than any human could flip switches or see or hear. So that's exactly what is captured on this particular slide. For machines where the user can press a button at any time, the machine samples the inputs faster than the user can press or stop pressing buttons. So, essentially the summary is we don't need to worry about it because a human is pressing or not pressing a switch or a button for the input because the clock is very fast in comparison. All right, let us move on to the two types of finite state machines. And by this time, you guys already know some or all the information that is presented over here. The top box says, does the output depend only on the current state or does it depend on the input? Right? That was the question. What do the outputs depend on? The first type of finite state machine was Moore, in which the output only depends on the current state. So they are called synchronous because the outputs change only when the state changes on the clock edge. So far we have seen only Moore machines. The other type of machine is a Mealy finite state machine, which also can change based on the current inputs. So it's inputs plus current state. These are asynchronous because the output can change when the state changes, also when the inputs changes. So it's asynchronous. And in this case, we actually write the inputs on the arcs of the state diagram. I talked about that briefly a while ago, but we'll see more examples about this. Any questions on this slide? This is just a quick review, sort of what we have already seen. All right, let's move on here. So this is a generalized block diagram for a Moore machine. What I want to point out here is the dependence, right? So if you see this, the outputs are dependent only on the current state, right? So in a generalized block diagram, you could have a combinational logic here. You could have some sequential elements over here for the state memory using some flip-flops. And you could have another combinational logic over here at the end, output logic. But if you have a Moore machine, then the only thing that controls the output is the current state. Notice there is no wire that goes like that, right? That's not there. Or I should say this. So that dependence is not there, right? Which is what makes it Moore. Outputs depend only on the state. So this could be, some flip-flops here. So typically edge trigger D flip-flops. This is, some combinational logic. These could be logic gates, could be muxes, could be nothing at all actually, could be none, whatever, like some combinational network. And again over here, gates, could be mux, could be decoder, whatever combinational logic you can think of, and could also be none, right? You guys remember here, present state was equal to output, right? So we didn't have anything in our combinational network at the end, but we did have an exclusive OR at the front, right? So in this example, this was exclusive OR and this was none. You guys see that? And then we had one D flip-flop there. Questions about the state diagram? Sorry, not state diagram. The state machine structure for Moore. Okay. We have a few minutes remaining. Let us try to look at a vending machine example. So we are going to design a Moore machine here in which it's supposed to be a vending machine that can take two different types of inputs, nickels and dimes. Those are the only two types of coins it takes. And it sells items costing 15 cents. That's it. That's all there is in this machine. Things that cost 15 cents. That's it. Now, some other things to consider with this vending machine is, if the user pays 2 dimes or 20 cents, the machine is very greedy, so it keeps the 5 cents. It gives you the item, but it keeps the change. We are going to ignore the clock in this example because we are going to consider that the transitions occur when the user inserts a coin. So the transitions between the states are happening based on a user input of a coin here. Another assumption that we are going to make with this vending machine is that the user must hit reset to restart the machine after it vends an item. Let's not do that. Let's do something like this. Well, let's do this. This is the complete state diagram. This is one option. You can come up with different options here, but this is one option for completing the state diagram for this particular Moore machine, right? Actually, you know what? Let's do this step by step so that you guys get a better understanding here. So the first thing that I'll do is I will talk about the states, right? So think about what states would you want in this machine. Now I am keeping track of the coins, right? So my inputs are what? Inputs are coins, right? And there are two types of coins, the 5 cents and the 10 cents. Nickels and dimes. How about output? Vending and not vending. Yes. So vend and not vend. Right. So this could be like a triggering event for a release mechanism, right? Like the vending machine release mechanism. So either you vend or you don't vend. Okay. But the coins are your inputs. And because I'm only accepting 5 cents and 0 cents, I don't even need to worry about 1, 2, 3, 4, 6, 7, and so on. I only need to worry about 0, 5, 10, and 15. Because at 15, I will vend the item. So let me push this up here somewhere. Okay. Next, I will start with circles to denote states. I said we need 4 states to indicate how much money does our machine have. 1, 2, 3, and 4. I'm going to call them, say, state 0. Oh, come on. State 0, state 1, state 2, state 3. Then I will say, what are those states? Well, the first state is user has entered 0 cents, 5 cents, 10 cents, 15 cents. States and their corresponding money that they have. And I said I must hit reset to start things off. So I'm going to draw an arrow here to indicate that I need to reset it to come to the initial state. Also, I'm going to encode my 5 cents as N for nickel and my 10 cents as dime for D for dime. Yeah. So how do I go from, oh, by the way, this is a Moore machine, right? So if it's a Moore machine, then my outputs are dependent only on the present state, which means the output should be written over here in square brackets typically. Don't give an item, don't give an item, don't give an item. You have 15 cents, you can give an item. So I have written down the states, I have written down the outputs. Now I am left with drawing the arcs, the state transitions. If I am in state 0 or state 1 or state 2 or state 3, I need to consider at least 2 cases for every one of those states, nickel and dime. There are other things as well. What if nothing happens within the next clock edge, right? So I also need to consider that. But I at least need to consider what happens when I get a nickel from state 0, dime from state 0. So let's start drawing that. I'll use black again. If I get a nickel, I go to state 1. Very simple. If I get a dime, I go to state 2. I'm done with state 0. Let's come to state 1. If I'm in state 1 and I get a nickel, I go here. And if I get a dime, I go there. You guys okay with me so far? You guys are, things are, all right, nice. If I'm in state 2, I get a nickel or a dime, I go to state 3. You see this? I'm not giving any change back, right? I'm considering 15 and 20 to be the same. I'm not giving any change back. So nickel or dime, I'm going to go to state 3. All right. Now I also need to consider from each state. Oh, by the way, if I'm in state 3, if I hit reset, I go back. Now from every state, I also need to consider what happens if I do not provide either of those inputs, N and D. What if I don't give any? So if I don't give any, let me draw them in brackets itself. Within the next positive edge or active edge of the clock, if I don't give you a nickel and I don't give you a dime, stay there. It's a self loop, 0 cents. It's a question in the chat box. If we wanted to dispense 5 cents change, can we not just do some fancy complement of S1? If you wanted to dispense 5 cents, we could. Like you could say, all right, let me have state 4 here of 20 cents in which I output 5 cents, right? So in this case, I have 2 types of outputs, vending, not vending, and change. So I could increase the number of outputs and deal with that situation. You are absolutely right. We could do that, but this is a simpler state diagram example. All right, where were we? Oh yeah, self loop. So if you are in state 0, that means you don't have any money entered into the machine. And within the next active edge of the clock, you don't give any nickel and you don't give any dime. In that case, you stay there. And also you stay there if you press reset. So N complement and D complement or reset, for all those cases, you will stay in state 0, starting with state 0. Similarly over here. N complement and D complement. You stay there. If you press reset, you go back here. Come back down to S2. No nickel and no dime. Reset goes back. You guys see that? And if you are in state 3, you stay there until you hit a reset. So if you don't hit reset, you will stay there. Now, in order to make things a little bit simpler, what I'll do is I'm going to erase all the reset arrows because I've included this main arrow here to indicate that no matter where you are, if you press reset, you come back to S0. So I can afford to erase all of this. I'm just erasing the reset arrows. And that's it. You guys see this? So this is how you would draw a state diagram from a problem statement given. I cannot erase them because I did. So if you have drawn them, that's fine. Absolutely fine. But I'm saying that you don't need to because you have included it over here. So this essentially indicates that arrow in this form indicates that no matter where you are, you press a reset, you come back to state 0. That's funny. All right. So all of that is essentially captured over here, right? You have the 4 states: state 0, state 1, state 2, state 3, and the nickels and dimes. We have already done this from scratch, so you guys should be okay with this. And when you are in state 3, that's when you will vend the 15 cents item and cheat the user out of their 5 cents. Maybe. Depends on whether you have 20 or 15. How would you make it so that, if you hit reset, it dispenses whenever, whatever change you put in, unless at 15 cents. Oh, in that case, you would have to come back, right? Here, let me show you how you would do that. I actually don't have it over here. So I have an example, in the next couple of lectures, we'll take a look at an example where you can do that. You essentially, suppose you are at 10, right? If you are at 10 and you want to give back your 10 cents, you would go back to 5, give 5 cents, go back to 0, give 5 cents again, right? So you would essentially come down one state after the other while dispensing 5 cents, and so on. And if you guys have operated older vending machines, you might have seen this, the coins coming in slowly. It doesn't give you all at once. It gives you one after the other after the other. That's what is happening. It's going from one state to the other back, as opposed to going all the way back. So you would have to have more states to come back. So we'll take a look at that example as well. All right, let's stop here. We will come back and continue with this example of vending machine. Wouldn't dispensing it require like another? Oh, wait a second. What happened here? All right, let me stop recording here and then I'll take questions.